Hallo und herzlich willkommen zu Data Science mit Milch und Zucker. Mein Name ist René Brunner und ich freue mich, dich in die faszinierende Welt rund um Data Science, Datenanalyse und künstliche Intelligenz zu entführen. In jeder Episode werde ich mit renommierten Experten sprechen und dir praktische Anwendungsfälle sowie die neuesten Entwicklungen aus der Welt der Daten näher bringen. Und das alles in Bezug auf den deutschsprachigen Raum. Also schnapp dir deine Tasse Kaffee, Tee oder was immer du auch bevorzugst und lass uns gemeinsam in die Welt der Daten eintauchen. Mit einer Prise Milch und Zucker. Hi and welcome to the podcast Data Science with Milk and Sugar. Today we have an English episode and I'm very happy to welcome Sruthi Radhakrishnan. She's an AI consultant at itemis, has experiences with knowledge graphs. We will dive in this topic today. We check automated links based on the tags. We go in graph DBs for LMMs, the hot topics right now, the graph embeddings which are used there. Also, we go a little bit in the differences between graph and vector databases, as she has knowledge in both topics, which will be very interesting. So welcome, Shruthi.
Thank you, Rene, for having me in this podcast. It's a pleasure to be here. Thank you for the introduction. As Rene already mentioned, I work as an AI consultant, especially in the domain of systems engineering. We also have a lot of publicly funded research projects and slowly transitioning into the customer projects in the company. I have a master's in information technology from the University of Stuttgart. I did my master thesis in this topic of knowledge graphs, basically systems engineering knowledge graphs, that is the traceability graphs, link prediction. As Rene already mentioned, it's like automatically connecting two components based on textual similarity, structural similarity, etc., etc. And can't wait to dig deeper into this topic with you all.
Thanks for the introduction, and I'm very curious about the topics today. So we could start, as you mentioned already, the knowledge graph is one of your basic topics and knowledge. You did also research in this area. So what are knowledge graphs?
If you Google what is a knowledge graph, basically, you get a ton of information because knowledge graphs are almost everywhere. To give you an example, if you are looking to buy something for your home in Amazon, it uses a knowledge graph in the backend, which is a recommendation engine. So you can think knowledge graph as a network of elements coming together. It has an overview of different entities that are put together in a connected way. This is my understanding of knowledge graph. And an example, as I mentioned, is Amazon's recommendation engine. So a knowledge graph has three main components, which are the nodes, edges, and the labels that are given to this particular nodes and edges. This forms a semantic network. If you are from a background of systems engineering, if you are from the background of healthcare or whatever, then you can also think of knowledge graph as an ontology where it helps us to view things more clearly in a connected entity world.
All right, and if we dive into the recommendation engine, I think recommendation engine has two sides. One is user-based and one is content-based. So here you would go rather on the content-based side or rather on the user-based side?
Mostly on the content-based side, basically, because as the field of systems engineering uses a lot of data from different aspects, this is mostly concerned towards the content on how these entities are linked together, what are the kind of topology that exists between these graphs, how can we model this data into graphs, basically. So it's more focused on the content-based side. But for the evaluation purposes, so if you have to evaluate this knowledge graphs based on domain knowledge or based on expertise, then the user is involved. But I would say in a day-to-day basis, I'm more working on the content-based side and only partially on the user-based side. I could say this is 80-20 basically.
All right. And then also probably you can, if you go to the content base, if you look, maybe also a recommendation engine, if you look for some tool, then it can distinguish between like Golf of Mexico, the golf, the car, and playing golf then with this. Because if you do a normal search on Elasticsearch, then it cannot distinguish the meaning and differences.
Yeah, so as you mentioned, semantics is also something which is very important when it comes to like understanding how graphs have been placed, how graphs has been modeled, and especially the meaning of the word, the context of the word also depends on the connected entities, basically. So this is where we do a lot of analysis to identify how we could kind of group this embeddings together. So if you are working with a lot of recommendation engines, then semantics is equally important than the structure, and the semantics in a graph are then determined by the connected components. As your example, so if it is like a golf ball, then the other entity which might be related to this is a ball, or you have a set of properties that are associated with this particular graph. For example, if you're using something like a label property graph, then you have different variety of labels. And so one of the things that pops up in the knowledge graph ontology world is that for which task are you building this graph for? Is it like a recommendation task? Is it like a task where you have to identify entities? Is this a task where you have to do transactions, etc., etc.? So it really depends on which task you're modeling this data for. So based on the task that you're solving or the use case that you're confronted with, this could be efficiently modeled and extracted as one layer above of the existing semantic knowledge graph, which has different semantics associated with each other.
All right. And what are the challenges when you have been working with knowledge graphs? What are the main challenges in this field, and how can you solve it?
So one of the main challenges that you're confronted with, especially in my field, is the ability to model data as a graph. When you look into the data, you could already see that it is fresh and it is a graph. You could see with a human brain that this is a graph, but modeling that into a structure that is well adopted into like a machine learning algorithm or a graph neural network, then that's the tricky part. So I would say modeling of the data is one of the very tricky parts, especially when the data is from a from a domain that doesn't have so much of retrievers or so much of information about how this is sketched and what has been sketched, etc., etc. So this is one of the major problems, modeling the data. With respect to data sets, I feel the graph community has given a lot of data sets to try out with, especially for different domains. So one of the groups that is actively involved is particularly SNAP, which is from Stanford. They do a lot of research. They give out a lot of data sets on working with graph databases. There are also a couple of open source projects like Milch, for example, also gives you a lot of graph based data sets to work with. So if you want to get started with graphs, I would say there is abundance of data. But when you model that to a domain, then modeling the data with respect to the domain knowledge, with respect to the connections, bringing all the things together, having an architecture, etc., is very important. So to answer your second question, the solution is basically what I mentioned just now. So in IT companies or in any domains, there is different concepts of storing data. So initially we had databases, which is basically a form of putting several keys and values or several tables, relational tables coming together. And then there were document-based databases like MongoDB coming into picture. And then now we have graph databases where we can store the data from multiple sources. So I feel having a data architecture that helps us to bring all this data together in a centralized or a decentralized way is very important. And one efficient technique that has been introduced is this data mesh that has been widely used in different companies. And there is also different strategies on building data lakes. For example, if you don't know what to extract from your knowledge because your domain is very widespread, all this data-based technologies and databases comes handy to solve this problem of bringing all the data together.
So are these data modeling, are these the standard challenges? Because if you, I see a lot of people, they start with data science and then they want to train the cool models. And then they see 80% of the work is to clean the data, to get the data, to prepare the data. And if you come now to the knowledge graphs, is this similar that you have removing null values, checking where the data is, or do you have specific preparations that you need a specific format, or you need to reduce the features, or some specific constraints which you have?
So you're 100% right. So 80% of a data scientist spends his life cleaning the data. So the regular pre-processing techniques also are applicable to the graph data. But on top of this, we also need to extract like features which are different from the traditional machine learning or deep learning data which we do for sequential data. Because if you have a look into graphs are in the non-Euclidean space, but all the machine learning and deep learning tasks are based on like text, audio, images, videos, which are in a Euclidean space basically. So this structural aspects of capturing all the nodes and edges in the graph needs for a little bit of more additional processing. For example, if you are solving for a link prediction task, which is basically like a recommendation system, then you might also need to create something called edge embeddings that needs to be computed at the later step. So while working with the graph data, you need to have a set of properties in addition to the input data that you have based on the task that you're solving. And after you have created the recommendation, then it is also equally important to have some post processing methods to show the user what they really want to see in this particular task that they're trying to solve. So, in addition to the traditional pre processing, we also have some extra processing, which is basically based on graph theory, the features that we extract, and post processing based on the task that you're trying to solve.
All right, then can you, like the edge embeddings, I think this is a little bit more specific. Can you dive a little bit in deeper what this is exactly, what it means?
If you're from the NLP world, or if you're from in general like different, if you have worked with a lot of like transformers and all those things, or even without them, embeddings are something that we are confronted on a day-to-day basis. So embeddings is nothing but a vector representation of your data. We all know that the model that you're training sees everything as numbers, which is basically vectors, which are kind of like all these matrices coming into picture. You have this functions that helps you to create what you want to create, or what you want to classify, what you want to predict. So in graphs, we have three types of embeddings. One is like graph level embedding, and then we have node level embedding, and then we have edge level embedding. This depends on the task that you're trying to solve, especially the graph based tasks. For example, if you want to do something like document classification, then that is where graph embeddings comes to picture. So you have documents from different domain. Let's consider, for example, medical domain, where you have documents about skin diseases, where you have documents about like brain diseases, when you have documents about different types of patient history, etc., etc. So everything is located as a graph. So graph embedding is something that captures all this information of different graphs. For example, single embedding for the whole skin diseases that we have, single embedding for the whole heart diseases that we have, and this is where graph embeddings comes to picture. And then when you have to cluster node wise, that's where we dive deeper into node embeddings. So in general, these embeddings also have different loss functions. It's both transductive and inductive training that happens in this graph neural networks, so called. And then we have this Notovec algorithm or deep walk algorithm that helps us to create this node embeddings for clustering the nodes. And then on top of next is the edge embedding, which is basically the vertices, which is basically the edges between two nodes. And this could be like average embedding. So you have like two nodes already computed, then you have to combine, identify the relationship between the nodes. You can use like average embedded, Hadamard embedded, L1, L2 embeddings to kind of create this edge embedding. So these are the three major types of embeddings that are used in graphs, and there are several algorithms to do this based on the task that you're trying to solve, as I said.
And now, thanks for the very nice introduction and explanation of all the graphs, the different embedding types. I think it was a really great overview, and it's also a good basis now to dive in a little bit to the LMMs, to the hot topics, because there you often hear graph embeddings. What is then the relations to LMMs, to ChatGPT? How can it be used in this context?
So that research is still like a very exciting research that's going on. If you're looking into graph-based LLMs, I think there is only one which is present in Hugging Face. It's I forgot the name, but you go into graph machine learning in Hugging Face. That's the only large language model that you find which is trained on like graphs basically. So what interests people when it comes to like LLMs and combining them with knowledge graph is this new field, which is like I wouldn't say it's new, but it's like a new trend which is evolving, which is retrieval augmented generation. That is combining the knowledge that you have in your domain. It could be like a PDF file, it could be like a document, it could be like an Excel files, etc., etc. Then you combine that with an LLM, and then you try to ask questions with the LLM, so it knows your knowledge and kind of uses how it's trained and gives you the answer. So this is the retrieval augmented generation. So what people are trying to focus more is that what if the data is not like unstructured, which is basically a document or a PDF file, and they want to have it as a graph. So what is the advantages of having graph embedding in combination with an LLM is that you can have this transductive dependencies because as you mentioned, graphs, as your example, there is like a golf ball, which could be a ball, which could be a game, etc., etc. So on using graphs, you can know this hidden information. So if you don't have to model the whole unstructured data, rather you can use pieces of the data which are connected with other entities that helps us to give even the undirected relationships that can be existing in the graph. So this transient dependencies are something that people are very much involved with, and people are they needed to kind of understand how this relationship is between different components. So it's to give you an example, one of the things that has been done by IBM Watson is that they took a collection of different cancer medicines that has been given to the world, and they started like seeing into different prescriptions for the same kind of treatments, for the same kind of patents that they had. And this algorithm that they built, which is basically like a set of connections, entities, etc., etc., started suggesting medicines that were having similar patterns in a different country, suggested by a different doctor, that had better results than the prescription that they suggest now. So basically, all those patterns that you evolve in these graphs are very much important for the LLMs to kind of be less hallucinative. So one of the main key reasons of using knowledge graph embedding with LLMs is that it reduces the hallucination problem. And I think there are like three different types of combining LLMs and knowledge graphs. One of it, which I gave as an example, and the other thing is that if you don't have an LLM that doesn't kind of give you like a question answering based on the knowledge, then that's also something that people are very much interested in kind of answering through knowledge graphs, creating queries using knowledge graphs, etc., etc. So this kind of relationships are very much important because the LLM is still in the problem of like hallucination, etc., etc., that could be solved using knowledge graphs basically.
Yeah, that's a cool feature, and that's why it's also very hyped or well used to use the graphs in LMMs because of the hallucination. The biggest weak point of LMMs, a lot of people talking about, and if this can solve these hallucinations, then it would be even much better. So now, then we can also jump over because now we talked about the graphs, graph DBs for LMMs, but I also heard that I know practical use cases which were used with vector databases, which can be also a good point. We also had a different podcast some time ago about these vector databases that these are trained for the LMMs also to prevent the hallucination. So what is the difference then between the graph and the vector database?
So, in general, graph databases were used to store these entities. So, they were basically traditionally they were built to solve the problem of several join operations that you have to do when you have to extract data from relational databases, and then to do like deeper analysis rather than graph databases. For example, if you have to find the shortest path in a document or SQL database, then the query is very huge and the time taken for traversing this graph is very huge. But graph databases were meant to solve this problem of storing connected entities together so that you can do deeper analysis, you can have lesser query, lesser length query, and lesser querying time with high scalability, etc., etc. And there is a specific concept of graphs which helps us to do this more efficiently. That's called indexing, basically. So these indexes are assigned to the entities that we put into the graph databases. After the advent of LLMs, or after people started noticing that what if we can store this whole embedding as a vector rather than disconnected entities, that changed the whole story. So when it comes to vector database is a place where all the vectors are stored for the particular entity that you want to vectorize. Let's say you're doing something like a clustering operation, for example, then this text that you're clustering is then embedded using an embedding model. One of the embedding model by OpenAI is Text Darwin-C or text embedding ADA002, which helps you to embed all these vectors and store in a vector DB. So what are the advantages of storing text that is converted into a vector DB is that you can run computations more efficiently. If you want to do like similarity calculation, if you have to do something with retrieval augmented generation, then you are reducing this one step of converting it each time into vectors. Rather, you store the vector at once and you perform all the operations in this vectors. And there are also several vector stores that started arising, like Fires, for example, which is from Meta, that also helps you to store even vectors that are very large than the actual size of vectors that you would create. So they are meant to do very quick transactions. If you are in an operation, for example, you're placing an order in Amazon, you're doing a financial transaction of paying your university fees, etc., etc. So you need more efficiency. So that's where all these vector stores are really, really coming into play, where you can natively run the operations on the vectors rather than converting them each time. So compared to graph databases, I think Neo4j has now a vector index, but I'm not like very sure. But I think like there was a blog post about like having a vector index in Neo4j. So they are trying to combine these things together, so you can search more efficiently, you can search more effectively, and according to the task, you can do computations more quicker than before how you would do in a graph database. So in when it comes to like vector databases, I feel there is a lot of combinations of things, and there is a whole lot of vector databases out there. So choosing what is right for your particular task, especially with the infrastructure, especially with the approximate nearest neighbor algorithms, which is the algorithm that runs behind the recommendation system or the similarity system of this vector databases, are kind of like natively known. And if they are very clear and very open about, if a vector database is very open about having such a open approximate nearest computation, HNSW, or what algorithms that they deploy, then it would be easier to choose whether a graph database or a vector database would be ideal for your use case. So for some of my use cases, vector databases were the best. For some of my other use cases where there is an introduction of like ontology, where there is an introduction of multiple connected entities, multiple stakeholders, then I feel graph databases are still better than vector databases.
What do you mean exactly with the graph databases, multi-vendor, or what does this mean exactly? Or can you give an example for this?
Yeah, graph databases also has multiple vendors basically. So we have like Neo4j, which is one of the most prominently used graph database. At least 60% of the graph enthusiasts use Neo4j. And then there is Tiger Graph, one thing that we use internally. And then there is ArangoDB, which is basically like document cum graph database, which is a mixture of both the things together. And there are a few more. There is dgraph, basically. So compared to different vendors, it's a matter of choice on how you want to see. So if it is about like licenses and all those things, then you have to really think about how to commercialize this. If you're using for research purposes, then Neo4j has an open source version. Then there is also Tiger Graph. So if you're working in a very, let's say, speed intensive or a very efficient way of transactions and all those things, so Tiger Graph is the best choice because they natively run the queries compared to Neo4j, because Neo4j has something called Cypher, which is like a graph query language that depends on APOC, which is awesome procedures on Cypher, to run all these algorithms. But it really depends on which use case you're trying to solve, how much speed are you willing to achieve, what is the commercialization aspects of the project that you're working on, and like so many other factors that you need to consider when you have to choose between different vendors when it comes to like vector databases or graph databases. So it really depends on the use case, I would say.
Yeah, this sounds very cool. Also for the explanation of everything. Thanks a lot. We went through a lot of topics like knowledge graph, what it is. We had the embeddings, different types. Today we had graph DBs, we had vector databases, we had even the vendor list overview. It's very nice of graph DB. So for the listeners, if you want to choose one graph database, I think there's some ideas out there which we mentioned of common graph databases. So we made a large topic today, and we're also reaching to the end. At the end, we always ask our participants we ask you for the participants of your main tips which you have for them. So 1 to 3 tips out there from what would you suggest for the people? Which challenge did you had, or if they start data science or knowledge graphs?
So one thing that I would, the main challenge for me was having like a lot of background knowledge in knowledge graph. So if you want to get started with knowledge graph, I would suggest to have a brief look into graph theory. I know we have gone through this stuff. I know we have studied this stuff from our school, but still like having this refreshment, having understood like how this loss functions and all those things work is first thing that I would suggest the audience, because that forms the basics even before you get into data science, especially when you want to work with graphs. And the second thing I would suggest is that to have look into like a lot of experts who are in this knowledge graphs. Of course, there are only like a very handful of experts that you could pick when you are choosing the domain of knowledge graphs. One of the lectures that I would suggest even today is the graph machine learning course by Stanford. That sets the base for doing everything that you want to do with the graphs basically. And then the third thing is to network. Basically, the graph community is always very welcoming. That's what I have seen, at least to my experience, whether it's like graph databases, whether it's like having some doubt with graph neural networks and all those things. There is like a whole set of people on LinkedIn who are sharing their knowledge all the time. So I would say like networking with people who are working with graphs also gives you like a perspective on what problems that they try to solve, etc., etc. And finally, I would like to say when you get started with, when you're starting out with data science and all those things, the only thing that I would suggest for you is that have a strong grip of what domain that you want to go. Like especially in AI, AI is currently the hype. But when I got into AI, I did a lot of computer vision. I did a lot of deformation reduction in different crystals and everything. So having a domain of your choice, whether it's medicine, whether it's like education, whether it's like finance or whatever. So having a domain that interests you, that puts you forward in doing things, and applying AI to solve a problem in that domain would be the most interesting thing to do.
That's the nice sentence at the end, to solve the problem and to help the others to be useful. Very nice. So thanks, Sruthi, for joining today, and also for your really insightful explanations and all the examples which you gave today. So thanks for joining.
It's a pleasure. You're very welcome. And thank you so much for inviting me to this podcast. And I hope the audience get something out of this and apply to solve their problems that they face on a day-to-day basis.
Das war's für heute in Data Science mit Milch und Zucker. Ich hoffe, du hattest eine lehrreiche und unterhaltsame Zeit mit uns. Vergiss nicht, den Podcast zu abonnieren, um die zukünftigen Folgen nicht zu verpassen. Teile ihn auch gerne mit deinen Freunden und Kollegen, die sich für Data Science interessieren. Wenn du Fragen hast oder dich in einem bestimmten Thema brennend interessierst, dann schreib mir einfach gerne eine Nachricht. Du findest mich auf LinkedIn, wo ich dich auch immer über neue spannende Themen rund ums Thema auf dem Laufenden halte. Zum Beispiel mit meinem neuen Buch Python Schritt für Schritt programmieren lernen. Außerdem findest du meine erfolgreichen Data Science Kurse auf Udemy. Du siehst, wir wissen, was wir tun, wenn wir wieder eine spannende Folge unseres Podcasts veröffentlichen. Vielen Dank für deine Zeit und dass du Teil unserer wachsenden Community bist. Bis zur nächsten Episode von Data Science mit Milch und Zucker.